All right, so for our fourth talk of the session, Trayan will tell us about hyper-separation logic. Are you connected?
Test. So, hey everyone, I'm Trayan, and today I'll be talking about hyper-separation logic, a joint work with Peter Müller and Thibault Dardinier from Zurich and EPFL, and I'm from INSAIT. So the goal of this work is to develop the first framework for modular reasoning for hyperproperties. What are hyperproperties? Well, hyperproperties relate multiple program executions together and characterize program behavior by doing so. For example, non-interference relates two program executions universally, that's why two universal quantifiers, and it states that for any two executions, if they have the same public inputs, then they must have the same public outputs. That is, there is no leakage of secret information. Another interesting hyperproperty is generalized non-interference, which is a weakened variant of non-interference to account for non-determinism. Its type is for all exists, which means that the hyperproperty states for all two executions, there is a third execution for which the three executions satisfy some relation. So the type shows how complex a hyperproperty is. And there are many other hyperproperties of interest. On the other side, we have separation logic, which is the gold standard for modular reasoning. Separation logic allows us to prove local specifications, and by applying the frame rule, allows us to augment said specification with an additional heap. However, separation logic is limited only to functional correctness, and the goal of this work is to lift the reasoning to arbitrary hyperproperty while preserving modular reasoning. Now, let's look at some existing program logics for hyperproperties. The most basic hyperproperty is for all hyperproperty, where the logic we all know is Hoare logic. For heap-manipulating programs, the standard logic is separation logic. For exist hyperproperties, the two standards are incorrectness logic and incorrectness separation logic, and so on and so forth. Recently, 2 years ago, Hyper Hoare logic was introduced, and it filled a gap for complex hyperproperties by the novelty of tracking set of states instead of simply states or k-tuples of states. We'll talk about why set of states are so expressive in the next slide. However, there was still a big gap, which we filled with this work, which is for complex hyperproperties for heap-manipulating programs. This is where hyper-separation logic comes. Okay, so it's important here to note that hyper-separation logic allows us to reason about different hyperproperties under the one singular framework. For example, if before we wanted to reason about for all and exist hyperproperties, we needed to use two different frameworks. Now we can do that with one singular framework. Okay, now why set of states are so powerful? Consider the following hypertriple, which has the precondition and postcondition colored in blue just for readability. So in our case, the pre and post conditions are satisfied by a set of states and not simply states. So our precondition in this case is satisfied by those set of initial states where all initial states sigma satisfy that x points to 5 and disjointly y is allocated. Then if we execute the program that at y we assign the point at x plus 1, then we end up with a set of reachable states where all these reachable states satisfy that x points to 5 and y points to 6 and they are disjoint. Now if we look at the following separation logic triple, which is the same as the above, but without the universal quantifier, it turns out these two have the same satisfiability. That means that we can express separation logic by just putting an extra universal quantifier. Now, if we look at the existential case, for example, here the precondition states that there exists at least one state sigma, which has R allocated. Then if we non-deterministically assign at R integer between 1 and 4, then it is clear that we will have at least one reachable state sigma prime with R still being allocated, but now pointing to 1. Without the existential quantifiers, we obtain exactly the validity of separation sufficient incorrectness logic. And for those of you who don't know, SSIL validity states that for all initial states, there is at least an execution trace that ends up in the postcondition. Yeah, so we can express SSIL with one existential quantifier. Now, let's consider the following relational separation logic triple, which expresses non-interference. For L being low sensitivity variable and H being high sensitivity variable. So RSL works just as normal separation logic, but for pairs. So we track pairs of states and not simply states. Here the precondition states that we start with the same low variable L, both first and second coordinate have L pointing to the same value, and we end up with the same value for O. That means that O doesn't depend on the secret H, which is exactly non-interference. We can express this RSL triple with the following HSL triple, where the precondition states that for all two initial states, sigma 1 and sigma 2, they both have L allocated, and moreover, it points to the same value n. Now we execute the program, and our postcondition states that for all reachable states, sigma 1 and sigma 2 primes, they both have O allocated and pointing to the same value. That means O doesn't depend on the secret H, it depends only on L, which is exactly non-interference. So in short, why set of states are so powerful? Because we can put restriction on this set of states in the form of quantifiers, and by doing so, we can express different logics, and even more, we can express hyperproperties which are not expressible by any current separation logic. For example, exists for all. Now, onto the key result of this work, the generalized frame rule. The key new thing is the new hyper-separating conjunction, which we'll denote with the following symbol. Before we see why this frame rule is so general, let's first see this restriction that we have here. We restrict that our frame should be consisting only of universal quantifiers, so no existentials. Why is that? Well, because an existential in the frame would enforce reachability in the postcondition, which in turn enforces termination. That's not that interesting. We will see that this is not a bad restriction. Now, why do you call it generalized frame rule? Well, because using our frame rule, we can obtain the frame rules of other separation logics and even more. For example, consider the following hyper triple, which states for all states sigma, so for all initial states, if they have x allocated and pointing to 5, and then we increase it by 1, then obviously all states will have x pointing to 6. Now, if we frame the green frame that states that all states have y allocated by properties of our hyperstar, which we'll see in a moment, in a sense, our hyperstar distributes over universal quantifiers just as normal conjunction distributes over universal quantifiers. Yeah, we obtain this. And now if we look closely at the top and the bottom part, this gives us exactly normal separation logic frame rule. That is, said concisely, we obtain separation logic frame rule by framing one universal quantifier. We obtain a frame rule similar to RSL for two universal quantifiers. For SSIL, we don't frame with an existential because the two witness executions might be unrelated. This is a bit technical. The important part is we obtain SSIL frame rule by framing one universal quantifier, which is exactly what our frame rule allows us, which is what I meant that our frame rule is, yeah, that this is not a big restriction. However, as I said, we go beyond existing frame rules. For example, the following hyper triple above, expressing that exists for all hyper property, we can, for example, frame for all frame. And what is even better, we are not forced to frame the same amount of quantifiers on the left and on the right, which crucially allows us to frame, for example, non-interference to generalized non-interference, which is exactly what our goal was, to obtain modular reasoning for hyperproperties, and so on and so forth. Now, the key challenge of this work is defining the hyper-separating conjunction. To see how we do it and why it's challenging, let's first consider the normal separating conjunction. P star Q, we all know, is we take all states from P, all states from Q, and if they're compatible, we combine them. So different separation logics have different type for this sigma, and different type requires a different definition for this combination predicate. So separation logic, incorrectness separation logic, and SSIL, the combination predicate for them is just disjoint union. For relational separation logic and other such relational logics, the combination predicate is just pointwise lifting of the disjoint union. That means first coordinate with first, second with second, third with third, and so on and so forth. However, for our case, it's not that simple. Why? Well, because we don't have ordering. We cannot do first with first, second with second. Sets don't have order. Second, the cardinality of the two sets could be different, and on top of that, one could be finite, the other could be infinite. It's not a trivial task to define this combination predicate. And yeah. So now to gain a bit of intuition about this combination predicate, let's look syntactically the following assertion. The assertion says that all states sigma have X allocated. Now, if we disjointly add to it that all states have Y allocated, intuitively this should be equivalent to the fact that all states have X and Y allocated and they are separate. So, as I said earlier, in a sense, the hyperstar distributes over universal quantifiers, just as normal conjunction does. But it is separating. For the existential case, if we have that there is at least one state with X allocated, and we add to it that all frames have Y allocated, intuitively this should imply that there is at least one state with X and Y allocated and they are separate. Y implication and no B implication, because on the left we have that for all states Y is allocated, while on the right we have guarantee only for the witness state. So, in short, our hyperstar should respect both universal quantifiers and existential quantifiers, just as normal conjunction does. The only extra thing is that it should be separating. With that said, we proceed to defining the combination predicate. Consider the following set of 4 states, in this case, SP, where circular sectors represent heap, so the bigger the sector, the bigger the heap. And cores represent stores, so different core, different store. What does it mean to disjointly combine it with the following set of 3 states? Does it make sense to equate this set of 1 state? Well, consider that SQ satisfies that all states have Y allocated, and let's say that this is the part showing that Y is allocated. As we can see on the right, Y is not allocated, but we said that our combination predicate should respect universal quantifiers, and it doesn't here because we don't have Y on the right. So we should refute this S. We do that formally by the following. We require S, the one on the right, to be a subset of SP normal star SQ. By doing so, so that means that all states in S should be at least as big as the states in SQ. But as we can see, this state in S, the green, is not as big as the green state in SQ. So we correctly refute this S. What about the following S? Now we can see that the universal quantifier is indeed respected, but what about the existential? Let's say SP on the left satisfies that there is at least one state sigma with X equal to 5. And let's say that the blue color represents that X is equal to 5. As we can see on the right, we don't have blue color. That means that, that means that the existential quantifier is not respected, so we should refute that, because as I said, the combination predicate should respect also existential quantifiers. We formally do that by requiring the following predicate, PLW, which stands for preserved left witness. And it states that all witnesses on the left, so SP is on the left side of the operator, so all witnesses on the left, so the blue state, should be preserved through a state on the right, so the blue in SQ, into S. Because now we have preserved the witness, that means we respect both universal and existential quantifiers, so this S should be accepted. And we have a symmetric preserved right witness if the existential quantifier was on the right-hand side. Okay, with the main contribution covered, we now turn to the smaller contributions. So first thing, we identify and solve two non-locality problems. That means two problems with the frame rule. The first one is about allocation, and the second is about errors. And for errors, we identify two types of errors: local, which means compatible with the frame rule, and non-local, which means non-compatible with the frame rule. We solve the problem with the non-local errors with the so-called unknown states, which unfortunately I don't have time to tell you more. Then we define hyper-triple validity and prove semantic rules sound, which is what we call hyper-separation logic. And finally, we define a syntax for our hyper-assertions and prove syntactic rules sound, which is we obtain a syntactic variant of hyper-separation logic. There is one more thing that is novel, is the so-called scaffold variables, which greatly eases the work with our syntax, and moreover, it allows for a stronger read rule, which is quite technical, but yeah, it's very interesting. And we formalize all of this in the proof assistant Isabel. And with that, I'll finish and give time for some questions. Thank you.
Questions?
Okay, so this is very cool. I'm curious about what sort of future work is going on.
I didn't hear what?
Future work.
So future works is concurrency and non-termination. And relational properties, yeah.
Hi, thanks for the talk. So if I understood correctly, like all the examples you showed, the resources in the separation logic were plain regular heaps. So I wonder how much of this generalizes to arbitrary PCMs, or like did you use extra properties of the heap that go beyond the basic PCM axioms for this?
So I believe that this general idea would hold for any type of PCM, because I don't show here, but there is this PLW and PRW actually stand for, they correspond exactly to subtraction, which in a sense lift us away from the concreteness of the model and just steps on top of the normal separating conjunction. So for whatever the normal separating conjunction works, the hyper separating conjunction should also work, just because it's very abstract. It steps on normal separating conjunction and normal subtraction.
Okay, cool, thanks.
Hey, thanks for the great talk. So maybe a kind of general question that would maybe apply to Hyper Hoare Logic as well. So if sometimes hyperproperties are used to reason about two programs at the same time, for example, when you do refinement. So could you extend that like state-based reasoning to reason about two programs at the same time?
So yeah, this is part of yeah, we are working on that.
So when you mention concurrency, maybe that also
yeah,
yeah,
all concurrency, relational reasoning, and non-termination. Yeah, but each one has their
Thank you.
Their difficulties. Yeah.
I actually have a question about the frame rule for the incorrectness or the SSIL logics.
Yeah.
It seemed to me, maybe I'm confused, but it seemed like when you're framing on a forall, when you're framing on a forall, it seems like the rule you end up with is not quite comparable to the standard rule in those logics, because there you would have an exist that spans over the entire pre or the entire post. Is that, am I getting that right? Or is
So for separation logic and relational separation logic, we require only the consequence rule. For SSIL, we need one extra step to drop away the universal part that isn't attached to the existential part. So yeah, there we need one extra rule, which is joint true rule.
okay. All right, let's thank the speaker.